In this video, we're going to be covering a proof of Eisenstein's criterion. So I thought we'd begin by just restating that theorem of Eisenstein. And Eisenstein's theorem is really a way of telling us when a certain or particular polynomial happens to be irreducible over the rational numbers. Eisenstein's theorem will sometimes pick that up. And so let's begin with a statement of the theorem. Let's suppose that f of x is a polynomial. We want it to have integer coefficients. And let's just write f of x as a sub n x to the n plus so on and so forth, plus a1x plus a naught. Then if f of x happens to satisfy these three conditions that we have listed, then we can conclude that f of x is irreducible over the rational numbers. So the conditions that we need to meet are, we need to be able to find a prime number p such that the following three properties are satisfied for this prime. So the prime number cannot divide the leading coefficient, which we're denoting here by a sub n. The prime number p must divide a sub I for all other a sub i's. So you don't want to divide the leading coefficient, but you want to divide every other coefficient that exists there. And last but not least, we want to assume that p squared does not divide the constant term, which we're denoting by a naught. So I think the proof of this theorem is actually quite long, so it may be helpful as we proceed to have written maybe on a separate piece of paper the three conditions that this prime p needs to satisfy. Now let's get started on the actual proof here. The way the proof is going to proceed is by contradiction. So what that means is, it's going to be kind of a mouthful to write down what that means. What that means is we're going to assume that the polynomial that we have, f of x, is reducible. So that's the contradiction part, that's what we want to contradict. But we're also going to assume that there exists a prime p that satisfies the three hypotheses that we just went over on the previous page. So we're going to assume that the polynomial is reducible, but we can find a prime p for which p does not divide a sub n, p divides a sub I for all other I, and p squared does not divide a naught. Now the first thing we're going to do here is we're going to use the reducibility. So we're assuming that f is reducible. So what that means, according to the definition, is that we can write f of x as the product of two different polynomials, g of x and h of x, that have degree at least 1. Right? And here's where we're going to use Gauss's lemma, which I didn't go over orally but was on the previous slide and is in the previous video. We can take this polynomial f of x and we can reduce it over the rational numbers. That's what it means for f to be reducible over q. And then Gauss's lemma is what tells us that we can actually assume that the polynomials g and h that we have integer coefficients. Now, the reason that that's going to be important to us is I want to define a ring homomorphism, going from the ring of integers to adjoint x to the ring of integers modulo p adjoint x. So I want to go from polynomials with coefficients in the integers to polynomials with coefficients in z mod p, and I want to do this in the natural way. That is, what I want to do is I want to start with a polynomial with integer coefficients, and what I want to do is I want to just reduce all those coefficients modulo p, where p is that special prime that we have satisfying the three conditions of Eisenstein's theorem. So here I'm just sort of introducing the map that I'm going to be calling phi for the remainder of the proof. And what I'm saying is that this natural map takes an element of the integers to itself mod p and just sends x to x. Now, here are the things that I want to note that are going to be important to us as we move later on in the proof. The first thing is I can take phi. We're assuming that f has integer coefficients, so f is a polynomial in z adjoint x, so I can take phi of f. And what happens when I do that is I'm going to write phi of f as a times x to the n. And all that a is just going to stand for whatever a sub n was, but read modulo p. I suppose I should say that the reason that that's true is everything else is going to vanish, right? When we're looking at phi of f, we're assuming that the prime p does not divide this leading coefficient a, but we're also assuming that the prime p does divide all the remaining coefficients. So even though we originally wrote f as a sub n x to the n plus a sub n minus 1 x to the n minus 1 and so on and so forth out to plus a1x plus a naught, each one of those terms, a1, a naught, a sub n minus 1, they were all divisible by p. And so when we take phi of f, all of those terms are going to vanish away, and all we're going to be left with is this a times x to the n. Right. The second point that I really want to make is that phi is a ring homomorphism, and we have assumed by Gauss's lemma that the polynomials g and h actually belong to z adjoint x instead of just q adjoint x, and therefore it makes sense to take phi of them as well. Right? And because phi is a ring homomorphism, we know that we can, and f is equal to g times h, we know that what phi of f is equal to, we know phi of f is equal to a times x to the n by part 1 here, but it's also got to be equal to phi of g times phi of h, since phi is a ring homomorphism. Okay. Now, the next thing is going to get a little bit cluttered here, and something's going to be a little complicated by the fact that this typesetting program does not make a really beautiful difference between an L and a 1, so just make sure that you're clear on that. But we have to get a little bit messy. I want to introduce some notation. All I've known up to this point is that g and h are polynomials of positive degree with integer coefficients. What I want to do is just sort of write them down as generally as I can. So what I'm going to do is I'm going to write g of x as b sub k x to the k plus so on and so forth, b sub 1x plus b naught. So in the same way that I wrote f, but I'm going to change a's to b's and n's to k's. And then I want to do a similar thing with h of x. I'm going to write it as c sub l x to the l plus so on and so forth, plus c sub 1x plus c naught. So that's the first part, is I'm just going to introduce that notation. The thing that's a little bit annoying is that my l's and my 1's kind of look similar here. And what do we know? We know that since the product of g and h is giving us the polynomial f, we know that each of k and l has degree somewhere in between 0 and n. Right? In fact, we know that k plus l has to be equal to n. We know that neither k or l is 0, since we're assuming the polynomial is reducible, and we know that neither of them is n for the same reason. Now, additionally, we know that a sub naught, which remember is representing the constant term of the polynomial f, it has to be equal to the product of the constant terms from g and h, since that's the only way that I can get a constant term when I'm doing this elaborate foiling process for polynomials. Right, so we know that a sub naught is b sub naught times c sub naught. By assumption, we know that p sub divides a sub naught, and p squared does not divide a sub naught. What follows from this is that p divides exactly one of b naught or c naught. Now, let me just explain that a little bit. P divides a sub naught, and it follows from that that p divides one of b naught or c naught. And all we're saying here is it can't divide both. If p divided b naught and p also divided c naught, then when I took their product and got a sub naught, I'd have something that was divisible by p squared. So it follows that p divides exactly one of b naught or c naught. And what I want to do is pick. Right? At this point in time, I have total symmetry between the polynomials g and h, and so it's really and truly without loss of generality, which I'm again writing as w log, that p divides b naught, and what's more, c naught is co-prime to p. Now, the way we're going to use this is as follows. Remember what our ring homomorphism phi is. We take phi of the polynomial g, and we just take a look at this polynomial g of x we've written, and we just read all of those coefficients modulo p. Because we're assuming that the constant term of g is divisible by p, that b naught term is going to vanish when we take phi of g of x. Right? And the resulting polynomial, phi of g, is going to have a whole bunch of terms in it where x is always present, multiplied by some sort of constant. What this means is that phi of g is divisible by x, and because we're assuming that c naught is not divisible by p, when we take phi of c naught, or phi of h, sort of distribute it and apply it to this C naught, when we read all these coefficients modulo p, that C naught is not going to vanish, and so phi of h is going to have a non-trivial constant term. The next thing I want to do is I want to note that the degrees of phi of g and phi of h are k and l respectively. That's because I'm not doing anything to the x's when I take a look at phi in this ring homomorphism. All I'm doing is reading the coefficients I'm reading the coefficients modulo p. And remember that the leading coefficient, a sub n, is not divisible by p, by Eisenstein's criterion, and that means that neither b sub k nor c sub l is divisible by p. If they were, then their product, which would give me the coefficient a sub n, would be divisible by p, and that would be a contradiction. So what that means is that b sub k and c sub l, the things I have written up there, neither of them is divisible by p. So when I take phi of g and phi of h, that b sub k is a non-zero number, that c sub l is a non-zero number, read modulo p, and so I'm not going to be able to sort of eliminate these leading coefficients by taking phi of g or phi of h. What else do I have written here? I say phi of c naught is not equal to phi of c sub l. That's kind of an abusive notation here. But what I really want to argue is that phi of h has at least two summands. So what I want to argue is that c sub naught is definitely different from c sub l. And when I take phi of h, this first term that I've got right here, this c sub l x to the l, is not going to go away. And phi of c naught is not going to go away. I don't know what's happening in the middle. Maybe some stuff comes along, maybe some stuff goes away. But this term right here is definitely not going away. This term right here is definitely not going away, and they're different. So phi of h has at least two summands. That's the point of this next sort of note. Part of the reason that this proof is rough is because there's a lot of observe this, observe this, observe this, observe this, now it all magically comes together. So I know that it may be a little bit hard to keep up, but hopefully if you're at least keeping track of things as you go, we're going to do a nice summary of the proof at the end that should help to clarify the overall structure of this proof. All right, let's keep going. We have one last claim that we wish to establish before a whole bunch of things are going to start to come together. But the claim that we want is that there is a term of this product, phi of g times phi of h, of minimal degree. Don't know what that degree is. It could be 0, could be anything up higher than that. But what we want to claim is that this term is obtained only by multiplying phi of c naught by the minimal degree of phi of g. All this is really saying is, if I take two polynomials and I multiply them together, so I mean for now you can even forget where these polynomials live. When I take two polynomials and I multiply them together, the term of smallest degree in the sort of foiled out expansion comes from taking the smallest term in one polynomial and multiplying it by the smallest term in the other polynomial. This is just a generalization of the fact that when you have sort of two polynomials with constant terms and you multiply them together, the only way to get the constant term is by multiplying the constants together. That's what I'm trying to argue here. There's some sort of term in phi of g times phi of h that has minimal degree, and the way that we get it is by multiplying together phi of c naught, which happens to be the smallest term of phi of h, and whatever happens to be the smallest term when we're looking at phi of g. Now the next thing we want to note about this is that this smallest term in phi of g has degree at most k, and k is a number that's strictly less than n. So there is a smallest term, or there is a term of, what I mean by smallest term is there is a term of minimal degree when we're looking at phi of g times phi of h, and this term of minimal degree has degree at most k, which is less than n, and the smallest term of phi of h is phi of c naught. Let me go back for 1 second. because I think having what G and H are written out in front of you might be a little bit helpful. Okay, so if we buy that when we take, here's how we were writing G and here's how we were buying H. We then wanted to take phi of these things. We knew that this B naught was going to vanish, right? And some other stuff might vanish too. We don't really know what's going on here. But we know that this term does not vanish, for sure. When we were looking at H, we spent a lot of time arguing to say, this term right here does not vanish, this term right here does not vanish, and I don't know what's going on in between. What I want to be thinking about is taking phi of G and multiplying it together with phi of H and saying, how do I obtain the term of smallest degree? What I'm trying to argue is, well, phi of C naught, we know that that doesn't vanish, so that's certainly going to be the term of smallest degree when I'm looking at phi of H. I know this term vanishes. There might be some other vanishing going on until here. The next thing that I know, or the only other thing I know about phi of G, is that this term does not vanish. So if I'm talking about a worst case scenario here, absolute worst case scenario is that everything over here vanishes. This is the only thing that survives when I take phi of G. And when I multiply that by the phi of C naught, then I'm going to get the term of smallest degree. That's what I'm trying to argue on this next page. And that's going to lead to our problem, right? This is going to be our problem because we know that the number k is a number that's strictly smaller than n. Worst case scenario, the smallest term in phi of G has degree k. If everything vanished except for that leading term, then the smallest term in phi of G would have degree k. The smallest term in phi of H we know is phi of C naught. And so the term of smallest degree when we're looking at phi of G times phi of H has degree at most k, which is a number that's strictly smaller than n. However, this is where we're going to run into trouble, right? Let's see. This is what we're saying. We conclude that the smallest term in the expansion phi of G times phi of H has a non-trivial coefficient and it has degree at most k, which is strictly smaller than n. This is our contradiction. What we're contradicting is the fact that we have a ring homomorphism, because when we take phi of G and we multiply it by phi of H, what we're supposed to be getting is phi of F. That's the ring homomorphism part. And phi of F was really easy to figure out because of all the assumptions we were putting on due to Eisenstein's criterion, right? We had argued way back in the beginning that phi of F was just equal to ax to the n, where this a is secretly a sub n just read modulo p, right? All the other terms in phi of F vanished away because they were divisible by p. And what I've just argued is that there has to actually be a term of smaller degree in phi of G times phi of H. That term of smaller degree comes by multiplying phi of C naught by the smallest degree in phi of G. So this is our contradiction. Our contradiction is that there's no way for phi of G times phi of H to be equal to phi of F once I put all these restrictions on what phi of F has to be due to Eisenstein's criterion. And this is our contradiction. Now, we're not quite done here. This is really the end of the proof. But what I think is helpful at this point, because there were so many notes, let's go back and let's do a summary of what the real strategy was in the proof. And let's see all of the different facts that we used from ring theory so far. So the first thing, overall, the whole proof is done by contradiction. So what were we assuming? We assumed that there was a prime p. We were assuming that a sub n and p was equal to 1. That should be a sub n right here, not a sub naught. A sub n and p were co-prime. The leading coefficient was not divisible by p. We were assuming that p did, however, divide a sub I for all other values of I, 0 up through n minus 1. And we were also assuming that p squared did not divide the constant term of f, right, which the constant term is a naught. But the part that we aim to contradict is we also assumed that f was reducible. The next thing we really used is we were assuming that f is reducible. Reducible over what? Reducible over q. So we wrote f of x as g of x times h of x, where g of x and h of x were polynomials in q adjoint x, and that's where we used Gauss's lemma to take f of x and write it as g of x times h of x, where g and h happen to be to lie in z adjoint x. So they had integer coefficients, and once we had that, we were allowed to apply our homomorphism to them. So we use this natural homomorphism from z adjoint x to z mod p adjoint x, which was just take all the coefficients and read them modulo p. Okay. Once we had argued that g and h belonged to z adjoint x, then we could apply phi and apply this property of our ring homomorphisms to say that phi of f is equal to phi of g times phi of h. And we use all of our different divisibility assumptions in different ways to investigate what would phi of f have to look like, what would phi of g have to look like, what would phi of h have to look like. And that was the part that went on for a long time, right? Different properties of phi of f, different properties of phi of g, different properties of phi of h. Then lastly, we used properties of polynomial rings and the way that we go about standardly foiling out and expanding polynomials to arrive at a contradiction. So we proceed by contradiction. What the contradiction is a mouthful because of the way that Eisenstein's theorem is stated. We used Gauss's lemma and a very natural ring homomorphism from z adjoint x to z mod p adjoint x. And we used the three divisibility assumptions that we had to investigate phi of f, phi of g, and phi of h independently. Then we used properties of combining polynomials to arrive at the contradiction that we needed.